Hi everyone, welcome back to AI Lit Review, where I break down AI papers in a way you can listen to and not just read. Today we're talking about Retrieval-Augmented Generation, or RAG, a 2020 paper from Facebook AI that completely changed how we think about knowledge, memory, and language models. If you have ever wondered why LLMs hallucinate, or how they can be grounded in real documents by the inputs that you write to them, this paper is basically the starting point. At a high level, RAG asks a simple question. Instead of forcing a language model to store all knowledge inside its parameters, as the recent at the period of 2020 has shown throughout, can we rather let it look things up by itself? So rather than mapping input text directly to output text, RAG splits generation into two parts: retrieve relevant documents and then generate an answer conditioned on those documents. So it is split up into retriever and generator. And the key idea is the whole process can still be written as a clean probability model, just like a standard language model. The standard language model is defined as probability of y given x, or autoregressively probability of yi given x, comma, tokens before yi, meaning each token is generated based on the input and previous tokens. RAG keeps exactly this goal. What it changes is how we compute the probability, so that it is factored into two parts, retriever and generator, which corresponds to p z given x and p y given x comma z. RAG does not change the final goal. What it changes is how we compute the probability. RAG introduces a latent variable z, if you can see the whole equation, which represents a retrieved document. So it is retrieved document z, or latent vector z. So instead of going directly from input x to output y, the model says, first decide which documents might help. First, let's find z. Then generate the answer using the z, not just x, but also z. That is what the whole equation means. And the summation at the very outer part of the equation is called marginalization over z. You can think of it as trying multiple pieces of evidence, lots of z's, and generating an answer with each z and given input x, and weighting them by how relevant they are, weighting them by p of z given x. Now let's unpack the retriever part. The retriever is modeled by probability of z given x. It has several different components inside it. First, a query encoder to embed the input. So input goes through the query encoder to produce q of x. And then a document index part with pre-computed embeddings, so that there are lots of z1 until z1, z2, and zn. An inner product search to find the top key documents. So q of x and dz goes through the inner product, and then top value of the inner product becomes the top key documents that q of x, or the input x, could actually refer to as an expanded knowledge, or the evidence or documents. You can call it whatever you want. Inner product between qx and dz works because it measures vector alignments, since they are both vectors, and it measures how much the input and document points to the same direction. This component is non-parametric, which means you don't have to train it, because the documents are external memory, not learned weights. You can think of this as giving the model a searchable memory, the extended memory, instead of forcing it to memorize everything inside of parameters. Let's go to generator part. The generator models p of y given x comma z, the second part of the factorization. It's a standard sequence-to-sequence transformer model, and it is conditioned on both the input x and the retrieved document z. The generator still produces tokens autoregressively, but now its reasoning is grounded in the explicit evidence, z. This is where RAG reduces hallucination and improves factual accuracy. The paper points out there are two ways to use RAG: RAG sequence versus RAG token. RAG sequence model uses the same retrieved document, so single retrieved document, to generate the complete sentence. The document Z is treated as one latent variable per output, and marginalization happens once per sequence. This is simpler, more stable, and cheaper, so that only after one sequence is generated, it goes to the next document to generate another sequence, another whole sequence. RAG token, it is using a different latent documents for each target token and marginalize accordingly, average them accordingly. And formally, each token marginalizes over its own Z of I. This is more expressive because one token refers to a lot of other documents at once, but also more computationally expensive. So in practice, RAG token is theoretically elegant, but RAG sequence is often preferred for efficiency. And the paper evaluates this algorithm RAG on open domain question answering, natural questions, web questions, fact-heavy generation tasks, and there were very key findings due to these experiments. And first one of them is RAG outperforms parametric-only models. So it means RAG outperforms all other LLMs. RAG generate more specific and factually accurate responses. So if you look at the task called MS Macro, let's look at the input, the question. Define middle ear, the RAG T or RAG S, which means RAG token and RAG sequence respectively. They generate really eloquent answers, like the middle ear is the portion of the ear internal to the eardrum. It is more eloquent compared to the BART model, which is a pure sequence-to-sequence model, parametric-only model. And you can pause and look at all the inputs and generations compared with BART and RAG. The second finding is effects of retrieving more documents has their significance only until a certain point. Retrieving more documents yields better results, but it isn't significant when crosses certain threshold. And figure 3 on the left shows that it shows monotonically improving, but performance peaks for RAG token at 10 retrieved documents. And then there are many other findings like updating knowledge is trivial. You can just swap the document index, no retraining required, which is given. And attribution becomes possible, which means you can trace outputs back to retrieved documents, and this is huge for trust and interpretability issues. And there is more thing interesting that the paper doesn't tell. We could tell this because after the paper is introduced, many people used RAG to develop their own systems, and they're become a different part of RAG reproductions, you could say. But most modern systems called RAG or use RAG do not follow this probabilistic formulation anymore, which is py given x factored into two parts, retriever and generator. It was very neat, but it is not used as themselves. And why? Because retrieval is now heuristic. Generation ignores marginalization, and documents are just stuffed into prompts. In other words, modern RAG is pipeline-based and not probability-based. So the clean equation is rarely implemented explicitly, but it's a trade-off. Modern systems optimize for latency, engineering simplicity, tool use, and multi-step reasoning. They sacrifice theoretical cleanness for flexibility. But even if modern systems don't strictly implement RAG, they still inherit its core idea, which is knowledge could be retrieved. RAG reframed LLMs from static models into reasoning systems with external memory, and that idea is still everywhere, and that was Retrieval-Augmented Generation. Thank you for listening.